Let me know when to start.
It has started.
Hi, everyone. So this is a presentation on P4OVS, a little bit of update and more on Linux networking overview that we have been developing since the last 6 months. So this presentation will be done by myself, Namrata, and I have Sandeep and Nupur from my team here, who will go on different aspects, and we'll do a small demo as well. So this is the agenda. We'll start with the P4OVS current architecture, more focus on the kernel control plane, going on to the split architecture that we've been talking about with the kernel control plane focus. Then I'll go over the Linux networking pipeline that we have developed and where do these tables get programmed from. Linux networking file and tables. Sandeep will go over a lot of details on the topology and the control plane packet design for P4TPTK, following up with the control ports and GNMI commands. And then Nupur will go ahead and show us the demo of how Linux networking on P4OVS is working and how all the kernel acceleration is working with P4OVS. To end with summary and some useful links. So this is the current architecture that we've gone through a number of times. So I'll just repeat a little bit here. So we have this P4 proto that we have been developing in parallel to OF proto. This is the OVS fork that we have brought in the IPDK GitHub. And in the P4 proto, we have been developing support for P4 runtime server, open config server that I've previously talked about. So today we will more focus on the kernel control plane. So this basically is implementing kernel acceleration. So what we've done is we've used open source the SwitchLink SCI module, and we've hooked up in the P4 proto. So what this does is this SwitchLink module will listen to the kernel control plane netlink commands. Will register to the netlink commands in the kernel to get updates from the kernel. And the SwitchLink will go ahead and program into SCI and Switch API and into the TDI target to get programmed on the either the IPO pipeline or the P4TPTK target. So this whole code is in P4 Proto. If you go in the P4 Proto directory, maybe I can show you here. Sorry. So the whole code is here. If you go in OVS directory, this is P4 Proto, parallel to OF Proto. And then you have the P4RT control for the P4 runtime and open config. The kernel control is for the SwitchLink SCI and Switch API that I discussed. And then we have this P4 Linux networking.p4. So this is what we are going to talk about. So we have been developing this P4 for basically acceleration of kernel, L2 forwarding, routing, ECMP, VXLAN tunnel, and CT, connection tracking capabilities. And you will see different components of these in different files. This is all compilable from the P4DPTK compiler and all integrated into the code using the SwitchLink, SwitchSci, and Switch API functionality. So here, so as I said, the kernel control plane, we register into the netlink messages. The netlink message comes in and gets translated into SCI calls, which is a standard interface. You can go and check the SCI APIs on, just Google it. And then this SCI calls will go into the TDI, which is the TDI is the table-driven interface, and it is also open sourced on p4lang/TDI. So this provides basically a target agnostic interface and a target dependent library that can be linked to the target agnostic part and called into the target. So this is all right now integrated in P4OVS currently with the current architecture. And from here, we are moving on. You'll see some updates on IPDK on the split architecture. So the main reason for this was to be able to program be able to program the P4 runtime open config and SCI components with OVS or any other custom switch as well, and to create a plug and play model, like where you could get the component running with SI or with P4 runtime or with open config all, or just one capability, and then work with TDI. So we will be starting open sourcing for this infra P4D from scratch. Probably first create an empty directory and then go on from there, adding, so this P4 proto here is basically the functionality that is translated into infra P4D in a cleaner format, where we'll also be upstreaming a lot of code, the P4 runtime code and open config code, into Stratum. As you all know, we have been using Stratum for the P4 runtime open config functionality, and we've been creating patches and pulling a lot of code in the P4 OPS integrated model, which we will be now pushing out the code, upstreaming the code into Stratum. So this is kind of a plug and play. Sorry, go ahead.
Namrata, I had a meta question for you.
Mm-hmm.
Question on the chat came up. Do you prefer questions midway through the talk, or would you rather keep all the questions till the end?
I can stop after every slide, so everybody has the context, and wait for questions.
Okay. All right. Yeah. And maybe Thomas, is your question on this slide, or is it the previous one?
Actually, it's both.
Okay. Sorry to interrupt you, Namrata, but when you're done with this one, we'll take a question.
Okay, so basically, so this P4 proto in the code here, integrated code here, becomes a separate daemon now, and is called infra P4D. This will have the same components, the P4 runtime open config and the kernel acceleration that we are going to talk about more, integrated in infra P4D in a plug and play format. These upper layers, application layers, are going to talk to TDI, the target interface, and from here on they basically call the functions to program your target. So we'd also developed some CLIs here, like the OVS P4 Kettle CLI that acts as a P4 runtime client, and the OP Kettle, what we call GNMI CLI, for the open config client to add configurations via GNMI. These clients are going to be infra P4 clients. These are going to act as controllers, and will be able to program into P4 runtime and open config servers. And then you can add any other P4 runtime capable manager to interact with infra P4D and to program into your P4 targets. OBS now will become a much smaller, basically a smaller patch that we'll be able to upstream into OVS. And this will basically take care of all the control packets coming up via ARP. All the control packets coming up like ARP, which need to be resolved by the OVS switch. And we will need the L2 table entries, and Sandeep will go over more on this stuff when he goes through his slides. So any communication between OVS or any custom switch into infra P4D could be P4 runtime message. This also talks to the SDN controller here. So we have a concept of exception packet. So something that cannot be handled by OVS and infra P4D, a missed configuration, can be sent up to SDN controller as a packet in. So these are the exception packets that go from infra P4D, P4 runtime client into the SDN controller. And the focus here is on kernel. So we have pulled up the switch link SI, switch SI, and switch API as well into infra P4D, and this will listen to the kernel notifications now and go and program the P4 target using TTI. I can take questions now.
Okay, thank you. So in your previous slide number 3, you show that there are 3 different targets in TDI, which are BPF, P4 IPU, and DPDK.
Right.
And then next slide, we see only DPDK. Does it mean that IPDK is supporting only DPDK as a target?
No, this is a DPDK/IPU.
Eh,
So all of these targets, these are just examples. There could be more targets, more vendors, right, who will want to integrate into TDI by creating their own target dependent library, which gets linked into the TDI. So there could be more targets other than what I've listed here as well. And here I have listed DPDK/IPU. We also have Tofino, and basically we can add any target which that supports TDI.
okay. IPU is a real target, or it's just a generic
Yeah.
name to say any hardware, any
So we
supported
have been
hardware?
working on Intel IPU
Uh-huh.
to start with, and yeah, so that's what the IPU here means.
Okay.
The
And
eBPF target is not as well enabled as the DPDK target because we are still in the process of having the eBPF target support the TDI at the bottom. So,
which target it should be? It would be Netronom
The
oh no, the
or
eBPF, yeah.
eBPF is purely in software. It's not a hardware target. So the eBPF is really similar to P4 DPDK, but we are still in the process of integrating its control plane with the necessary pieces that you would need to fit into the stack.
Okay.
Yeah. So basically, the target that we have open sourced and made everything work with is P4DPTK, because P4DPTK is open source, and that is why you will see examples of P4DPTK here on how to get things working. But everything should work similarly on IPU with minor changes, or eBPF as well.
Okay, thank you. I have another question on this slide. So we can have P4 runtime or use OpenConfig. I don't understand when to use which one. What
Okay,
are the
so
benefits?
So what we are using P4 runtime for is to program the pipeline into the P4 target. So we write a P4 and we create all the artifacts, like all the JSONs that go into programming your target and your middle layers like TDI and P4 info. So P4 runtime takes care of that by programming the pipeline and then adding into the tables in that pipeline. So add a flow, delete a flow, add counter, delete counter. If you see the P4 runtime, P416 spec, that is pretty much what we support in the proto for P4 runtime. So meters is another example that we will add support for later. For now, counters and set flow, get flow is working. So OpenConfig is mostly used for programming configurations and fixed functions. And the one that we have been able to open source is the addition of vhost ports and tap ports. So if you want to add a tap port into your P4DP ticket target, you would issue a command, a GNMI CLI command that will add a vhost port or a tap port into your target. So this is basically configurations. And this is for flows, for traffic.
Okay, perfect. Understood. Thank you.
Okay, I'll go to the next slide. So these are the components. As I explained, we have infra P4D and we have P4 runtime and open config server functionality. What we want to do here is we want to minimize the memory footprint and stratum for the IPU targets. So basically optimize everything that we have done so far. And then this integrates with TDI. We have been able to open source this in the P4 OBS. Now all the BFRT calls, you'll see we are making actually TDI calls in the code. So TDI is integrated in the open source P4 OBS. Then we have interface to the target backend via TDI, OBSDB client for port read. So if something gets programmed into the ports and we need to read that from OBS, we can add an OBSDB client, plug and play client that can be spawned and which can listen to the OBSDB server messages. Then we have We have plans to generate a P4 client library code that will work with this infra P4D, which could be integrated in any application like the IPU manager application that I showed. And it will be initially in Go and Python and maybe in C++. Then this infra P4D is also the owner of Linux networking.p4, the example file that we have created for kernel acceleration. And this drives the kernel configurations via P4 runtime. So what we do is when we bring up this Linux networking or the SCI part of the code, this will add the Linux networking P4, and we will be able to and provide the add delete rules that are in the P4 file. Then we have an interface to OBS for getting the L2 table entries in the inner bridge. This can vary from switch to switch, and the functionality can be added based on what the switch provides. For OBS now, the patch will become much smaller, and we will have the P4 runtime client integrated in OBS, along that will provide the L2 bridging details into the infra P4D, or any open flow rules that are in the control path and that are managed by OBS. Then we have the interface to the kcontrol P4D using the OBS DB. So we have infra P4 clients, infra P4 kettle, which is the P4 runtime client, and GNMI CLI, which is the open config client that is currently integrated with P4 OBS as infra P4 clients, and any other control plane here that can be added. So going on to Linux networking P4, so this is what we have developed so far as an example of how do we offload kernel routing and tunneling capabilities into the target data plane. So the first table here is the control plane table, which is basically sending the packet up to OVS. So we use VLANs for that, and Sandeep will go over in a lot of detail on how these VLANs are mapped to the tap ports for transferring the data to and fro from OBS to the P4 pipeline. So our packet or any other packet that needs to be processed by OBS will go through this control plane vport to VLAN map table, and the packet will be sent to the particular VLAN in the control flow. If the IP packets and the table is already programmed, we have the L2 table, L2 forward table, and tunnel encap. So this determines that the packet needs to be encapped, and the action here is encap sent to port, matches on the MAC address. From here, so you'll see some tables in parallel just to show that if the target data plane supports some parallel capability, then you could have this functionality running in parallel as well. For DPDK, we have it serial for now. So from here, as the color coding right here, so the color coding explains where these tables are programmed from. So if it's yellow, it is programmed manually from the TDI or P4 runtime. And if it is gray, then it is basically coming as a kernel update. So the switch link, netlink kernel update into the code and getting programmed from there. So your L2 forward and tunnel encap rules and all the action, the encap action, all comes from your kernel when the VXLAN is configured in the OBS or the kernel. So this will be sent up as the netlink message and get programmed into the P4 pipeline. And same as with L3 routing, we have L3 routing table that matches on IPv4 dest. And this is basically uh, uh, this basically determines where the packet needs to be routed for and sets the next hop IDs. We also implement the kernel state table. So this is basically a small initial example of the TCP state table pipeline, or it is, or you could use it completely for UDP pipeline. We have the CT.P4 and LNW CT.P4 that goes through these transitions and basically adds a table into the CT auto add table. So this is an exact match 5 tuple. that gets added based on what your state table is. So basically here you see that there is an auto add capability that we have used to demonstrate this is a PNA construct. This whole file is written in PNA, which is the portable NIC architecture, and auto add capability is basically one of the PNA additions, uh, which is not there in PSA. So this basically manages your firewall security rules and goes on to the hash block for ECMP. So there's a hash block here that can be calculated. This hash block can be set in the P4 file, and this capability is it can be installed as an action selector or a 5 tuple hash block that matches on UDP and carries the hash data in the metadata. So from here, we move on to the ECMP table. So either your next hop can be determined directly by your L3 routing table, if you have no ECMP, or if there is ECMP, basically this hash block will be used to determine what the next hop ID is here. So this is where you go and hit your next hop table. So these tables are designed in a way where you're you know in an efficient way where how you can offload all these routing tables from your kernel to your P4 target. So this next hop table basically will set the neighbor and the ref IDs, the routing interface IDs. These are the two tables that provide the outer test MAC. So here we encap the packet. So we start with encapping the packet, and this routing is on the outer header. And then for the outer header, now we need the outer test MAC and outer source MAC, and that comes from the kernel neighbor table and the ref table. And also the concept of exception table, sending any packet to this table could be basically anywhere in the pipeline. And this is going to do a packet in to your P4 runtime, send it up the stack. So after you have built a complete packet with the outer test and outer MAC, the packet goes out to the wire. So this is the VM to wire TX direction. Um, for a packet from VM to VM, we will go from the TX direction into your RX pipeline to go into into the VM. So this is your egress pipeline. Any questions here?
I had a question from the Slack, and maybe it's just a pointer to the documentation. Is that when you had the wire port, how did you add the wire ports to the P4 OVS? Is it the same? Is it the same mechanism we use in regular OVS, where you add it to a bridge or something like?
Yeah.
Okay, so it's exactly the same as.
So basically, the wire ports are basically these ports are going to have the tunnel interface, the tunnel set on the external wire ports, and these are something in the kernel that you have. So these ports actually, Sandeep will go over more on this. He will exactly explain how we get a packet into the wire port and how we transition it into the OVS stack. Exactly. But yeah, some ports are added into the kernel and some are added into OVS. So overlay ports are added into OVS.
Cool. That's great. Thank you.
Okay, so moving on. This is the RX direction pipeline. So here the packet is coming from the wire. It's coming from the wire, so it's coming in the VXLAN tunnel port. So we need to have a decap. So this L2 forward tunnel table will decap the packet, and the action is to decap and send to port. Control flows, as usual, will add the VLAN tag and will be sent to the OVS for processing. And this will go on to the CT state table again, add into the CT auto add table. For the security flows, this could be a common table between your RX and TX, and the same as exception table. So this does not have routing because we don't route on the inner header in this pipeline. You could very well add that if that is your use case. So this basically is just giving an example of how we are offloading from the kernel, and this P4 can definitely be extended to a lot more to support a lot more use cases, which we'll see like FRR in future. So if anyone wants to take this up and implement any more capabilities, they can feel free to contribute to the open source as well. So next, I will hand over to Sandeep for a deep dive into this Linux networking P4 and how the ports and control ports and all the flow is working. And then Nupur will take up from there and show you the demo. Sandeep, do you want to present from your own or do you want to control from here?
Somehow the present option is disabled for me, Namrata.
Okay, so can you request for control?
Yep, I will go ahead and I will add you momentarily.
Okay.
Apologies for that.
No issues.
All right, you should be able to take control now.
Yes, I have control. Thank you. Okay. You guys are able to see my screen, right?
Yes.
Okay. Hello all. Yeah, so thanks Namrata for the introduction and deep dive in the technical details. So let us start with a P4 program that we are talking about till now, Linux networking P4 program. So this is a apply block of a P4 program that we have going to target today. And this P4 program has an intelligence of differentiating between our host to network packet, which is our TX packet, and also network to host, which is our RX packets. Apart from this direction intelligence, it also has an intelligence to differentiate between control packets and the data packets. Remember the target that, I mean, the work that we are doing for now is mainly onto our L2 forwarding. So the current intelligence of control packets that we have is understanding an R packet. So any R packet that is coming to our DPDK target, we will treat it as a control packet and move accordingly. So this is a snippet of an RX pipeline. Oh, sorry, this is for TX pipeline where any packet that needs to go from an overlay network or underlay network, it will hit one of these rules and then it will go out of your box. If it is a control plane packet, it will hit your TX control VXLAN packet or TX control packet. If it is coming from OVS to VM, it will hit TX control packet table, or if any other data packet, it will hit your L2 forward TX table, and subsequent tables will be hitting based on your overlay packet or underlay packet. Similarly, if there is any packet coming from your wire to your house, it will be either it can have a regular packet or a tunnel packet based on the what type of packet, again a control packet or a data packet, it will hit these tables and the packet will be sent up to your underlay port or your overlay port. So this is the SAI integration that we have done to our P4 OVS, where these are the SAI calls that are being made, where kernel receives a switch link netlink message to our layer, which is called a switch link. From switch link, message will be translated and sent to your open sourced SAI SAI model. From SAI model, we make a calls to a switch API layer where it talks to your different targets. So in our case, currently we are targeting DPDK target. So any event that we get from the kernel, it can be either your static events like you create a port, or a dynamic events where you have learned an ARP entry or an FTP entry on OVS. We get those notifications to the switch link or switch SAI layer, where these calls will be made. From here, we go ahead and talk to our backend target, and then we program these particular tables. So if you see here, these are the events we are targeting. So these three events which are listed on this slide are static events where user has programmed something on kernel and that triggered an event on OVS, which went ahead and programmed few tables on your backend. One of them is underlay RIF for your tap port. So this port will be acting as your tap termination port. The moment a tap termination port is created, we get a notification. We go ahead and populate L2 forward RX table and with action as L2 forward, saying going forward, any packet that is coming with a destination MAC as your tap port, the packet should be directly sent to your this particular underlay port. Similarly, if there is any IP address or a route configured on top of this tap port, we make a calls to your create next stop SAI call, which updates local cache, but it doesn't actually go ahead and program anything right now. And if there is any route that has been configured on this particular tap port or a tap termination port, this goes ahead and programs these four tables, which is our IPv4 table with an action as set next stop ID, your RIF mod table, RIF mid, and RIF last table. This is basically to determine what is your source MAC from where the packet should go out. Similarly, once we create a VXLAN port, so this VXLAN port will be created by a OVS VSCTL command. It is the legacy OVS command where it goes ahead and attaches a VXLAN tunnel port to your bridge in OVS, and also it goes ahead and create a netdev in kernel. So the moment a netdev is created in kernel, we get a notification, and then we go ahead and make these SAI calls. One is create tunnel and create tunnel termination table, which eventually programs these tables, VXLAN encap mode table and IPv4 terminal termination table with their respective actions. So these are the static events that we get from the kernel, and we also get few dynamic events. Few can be from your underlay ARP learning, and few can be from your overlay or your OVS FDB learning. I will clearly talk about what FDB learning that is happening here. Why are we talking about FDB learning? When we look at our topology, we'll get more clarity on what is this FDB learning, why there is an FDB learning on VLAN NetDev and also a VXLAN NetDev. For now, let us see what are the events that we get once an ARP is learnt on your underlay. The moment an ARP is learnt on your underlay, it will basically tell what is your peer IP address and also what is your peer MAC address. Based on those information that we fetch from your ARP, we go ahead and program these tables in your backend. One is your neighbor mode table, next stop table, and L2 forward TX table. Similarly, once there is an FDB learn that has happened on your OVS side for a VLAN netdev, we go ahead and program L2 forward TX table with action as L2 forward, with where the port where it says is overlay port, and similarly L2 forward R external termination table where it sends the packet to your overlay port again. And also there can be learning happening on your FDB. Your FDB learning can happen on your VXLAN port, where we again call your create FDB, where it also populates your L2 forward TX table, and the action is set tunnel. Here, if you see, there is a little difference. The regular packets will be having L2 forward as an action, but your tunnel packets will have an action as set tunnel. So mainly these will be for the packets going within VMs of same host. This action will be for the packets which should go out of your current host. Any questions in these two slides? Okay. So just to reiterate, these SAI calls which we are seeing here are being taken from your open compute SAI layer, where the SAI definitions are already defined there. We have leveraged those definitions, and then we have integrated our switch link layer to make a similar calls to SAI. You can have any other application above the SAI to make similar calls, and it can go ahead and program our backend. So this is the topology that we are targeting today. So if you look at this topology, it's on a single host where we have our P4 OVS, which also has P4 SD, which is a P4 driver stack. And internally, it also has which is for a DPDK target. If you look at the communication between P4 OVS, P4 SD, and DPDK target, it is via your TDI calls. Here, we also have a layer, which is a switch link, switch SAI, and switch API layer. These are the three layers which we are targeting for now. These are the three layers which will give us more intelligence of your dynamic and then static learnings that are happening on your kernel and how they go ahead and program your backend. So if you look at, we have a netlink framework where all your kernel notifications will come to your switch link layer, and then it goes ahead and programs your backend via TDI calls. Similarly, an FDB learn that is happening on your OVS also makes a call to your switch SAI, switch API layer, and then it goes ahead and programs your target. Here, we also have our two utilities that OVS gives for the user. One of them is your OVS P4 kettle. Another one is your open config client, which is your GNMI CLI. The role of this OVS P4 kettle is to program your control plane rules and also to program your pipeline. And role of your GNMI CLI or open config client is to program your ports and also to link your physical ports to your control ports. I'll talk about different type of ports that we are supporting for now. So this is our DPDK target. Here, if you look at, we have multiple ports. One or few ports are connected to our VMs, or these ports, there are VMs spawned on top of these ports. And then we have few tap ports, and then we have physical ports. So basically, we use GNMI CLI to configure vhost user ports, and then we spawn a VM on top of this vhost user port. And we have also provided a CLI to go ahead and create a tap ports where this tap port will be attached to your DPDK target, and also there'll be a netdev created on top of your kernel for any interaction with the kernel that you want on this particular tap port. And we also have a physical ports here, port 0 and port 1. We have given a mechanism where you can have a corresponding control port for these particular physical ports. Here, the tap1 port will be used as a control port for your physical port 0, and tap2 port will be used as a control port for your physical port 1. Remember, when I say it's a control port, it doesn't mean every packet coming onto your physical port 0 should go to your tap 1, and every packet coming onto your tap 1 or tap 2 should go to your physical ports. These are also again driven by the rules that we configure on your pipeline. I can very well go ahead and program a rule saying that port 0 packet, few set of packets should go to my tap 1 and few set of packets from port 1 should go to your tap 2, and remaining packets need to be dropped. It is all driven by the pipeline. So on this topology, if you look at to your top left, we see an OVS running on our host, where we see multiple VLAN net devs are available, and these VLAN net devs are assigned to a single bridge. Also, we also have a VXLAN port, that is VXLAN tunnel, that is been created and it is assigned to a bridge. So the moment OVS VSCTL, we use OVS VSCTL command and create a VXLAN port, it goes ahead and create a kernel netdev also with similar to this. Like if you configure a tunnel with a destination port as 4879, it goes ahead and creates a netdev with VXLAN sys 4879. These are the netting notifications we'll be listening to. We'll be listening to your VXLAN sys port for configuring tunnel configurations. The static configurations, we'll be listening to the tap ports, which act as your tap termination ports. These tab 0 will be basically used just as a control port to move packets across your VMs to your OVS. Like, how do we do that? We go ahead and program few set of control rules, which would say any packet. When I say control rules, it always meant only for ARP as of now. So any ARP packet coming from your VM1 on the pipeline, we with OVS P4 kettle CLI, we go ahead and program a rule saying that any packet coming from VM1, add a tag and then send it to your control port, which is tab 0. The tag will be decided based on which VM the packet is coming. If the packet is coming from VM1, we add a VLAN tag of 1. Any packet coming from VM2, the pipeline adds a tag of VLAN 2 and then sends it to the same tab port. Here, on top of tab port, we would have created multiple VLAN networks with a VLAN assigned to it. And these VLAN networks will be added to your OVS bridge. That means any packet coming to your tab 0, because it has a VLAN tag, it goes to your VLAN network. Based on what type of packet it is, it's a broadcast packet or anything, your OVS will have control of that port, and then he will take a decision to either send the packet on other VLANs, or if he has already learned that MAC of that packet, he will either directly do a unicast to those particular ports. We will see that on a quick animation how we have done this, or how the packet moves across when sent from your VM1 and how it reaches to your peer host on a VM1. Okay, any questions on this topology?
So to restate sort of your setup is that does OVS look pretty normal on the left-hand side? It's just that you have instantiated this P4 pipeline sort of beside it that happens to see the packets first on the Ethernet side and is able to do some processing. And if it's unable to process it, it just pushes it to OVS. Is that how it works?
Yeah, so any packets, any external packets that are coming, if it doesn't hit any rule on your pipeline, it will be either sent to your exception port or it can be dropped. But for the control packets that we are getting to the pipeline, it will be sent based on the control plane rules that we have programmed. If we have not programmed, even in that case, based on a P4 file, it can either be dropped or sent to an exception port, or we can take any action there. But for now, we are not processing. I mean, if it doesn't hit any rule, the packet will be dropped as of now.
So to answer your question, Dan, I will add a few things here. So OVS is exactly how it works as stock OVS. So we have created this bridge, and then we have added these vports and VLAN net devs that map to your VM. So this is all needed because your P4 OVS basically works with the Open vSwitch kernel module. So it listens onto the net devs rather than the vhost ports. So any packet that needs to be sent from the VM from P4 DPTK P4 pipeline to OVS needs to go through these tap port framework, which maps to your vhost ports and the external ports. Go ahead.
Yeah,
Sandeep.
I just wanted to call out the it works very similarly to other offload mechanisms in OVS. It's just that you are sort of replicating the entire state of OVS in the P4 pipeline with that P4 Linux networking pipeline, and then just the control exceptions are going into OVS. There's no fast path, slow path split.
So now the whole slow path is basically, you can think of it as offloaded to your Linux networking pipeline, and only control packets go to OVS.
Cool, thank you.
Go ahead, Sandeep.
Yeah. So I have removed multiple components here just to see how packet traverses between our VMs. So this is basically our broadcast packet that has been sent from your VM1. It's trying to reach to host to VM1. So once the packet is generated from your VM1, the packet comes to your DPDK pipeline. Here, based on our control plane rules, we add a VLAN to this packet. Because it has come from VM1, we'll add a VLAN as VLAN1 and send it to a tap port. Here, the tap port, since it also has the sub ports or sub interface ports or your VLAN net dev, since the packet came with VLAN 1, the packet goes to your VLAN 1 net dev. It is a broadcast packet and it reaches your OVS. At this very moment, OVS goes ahead and learns the MAC address of your VM1. It programs its FDB table with VM1's MAC address and says that packet has reached from VLAN 1 net dev. At this very moment, P4 OVS will get kicked in. It goes ahead and program a table onto the backend saying that any packet with VM1 MAC that needs to go out, or he's receiving any packet with VM1 MAC as the destination MAC, that packet should directly go out on your vhost 0 port. That's what we tell here. This is the match key VM1 MAC, and the action is go to your vhost port 0, which is your port connected to your VM1. Now, since this is a broadcast packet, this packet will be sent to every other port on the bridge. And also, since we have attached our VXLAN port also onto the bridge, this packet goes to this particular VXLAN port and also all other VLAN net devs. Now the packet coming from your VLAN net dev reaches its tap port, and also the VXLAN port reaches its kernel. From there, it reaches the TEP port. Here at this moment, if the TEP underlay connectivity is not available, kernel goes ahead and makes sure the underlay connectivity is available. It learns the ARP, and so that the packet can be encapped and sent out of your physical port. The moment your underlay connectivity is learned, we go ahead and program these particular tables. The moment underlay connectivity is learned means we have received an ARP learn on your tap1 port. P4 OVS gets those notifications and it goes ahead and programs these tables on your backend. So now the packet that is coming from your tab 0, now based on the control plane rules that we have programmed earlier, the packet going from VM to tab 0 should be added a tag. Similarly, the packet coming from tab to your pipeline should strip off the tag and send to a vhost user ports. Here, the packet coming on VLAN 2 netdev comes to your tab 0, and then the packet with the VLAN comes to your pipeline. He strips off the packet and send to your vhost port where the packet reaches your VM2 without any tag. And also, similarly, the packet will be encapped because the underlay connectivity is already done. The packet is encapped and sent to the pipeline. Here, based on the control plane rules that we have already programmed, saying that any packet coming from port 0 should go to tap 1 and vice versa from tap 1 to port 0. Since it is again an ARP packet, this particular control plane rule will get kicked in and the packet will be directly forwarded from your port 0 physical port. Now this packet has reached on the wire and is reached your host 2 where your P4 OVS is again running there. Now let us see how the how OVS reacts and what are the notifications or what are the tables populated once it receives an ARP broadcast packet or a tunnel ARP broadcast packet. The moment ARP broadcast packet is reached on your port 0, it goes to your pipeline. Again, it's a control packet. It goes to your tap 1 port. From there, the packet will strip off the outer packet and the inner packet will go to your kernel. And this packet is attached to your OVS. Again, this packet goes to your OVS to the bridge. Here, OVS also learns the MAC address of your host 1's VM1 MAC. Here, the packet that is learned is on VXLAN port and it's host 1 VM1 MAC. At this very moment, P4 OVS will go ahead and program a table on your target which saying that any packet that needs to go to VM1 MAC, host 1 VM1 MAC, that need to be encapped here. If you see the action from your previous packet and now the action is different. Here, since it has received on your VXLAN port, the action is set tunnel action. Now, since it is a broadcast packet, again, the packet will go to all VLAN net devs. From there, it goes to your tab 0 port, which is its parent port. From there, the packet will remove the tagging in the packet and send to all the VMs that are been available on your host 2 machine. Here, VM1 is the one who is destined to receive this packet. The moment he gets an ARP request from your VM1 of your host 1, he goes ahead and replies back with an unicast ARP reply. Now this is a unicast ARP reply path. Here again, our control plane rules will get kicked in. Since the packet is from VM1, the packet goes to your tab 0 port with a tag, and the packet from tab 0 port goes to VLAN 1 network, from there to your OVS bridge. Here we go ahead and learn your VM1 MAC on your host 2. Host 2's VM1 MAC will be learned, saying that it has reached on VLAN 1 network. Going forward, the packet should go any packet with destination MAC as VM1 should go to vhost port 0. Remember, this is an unicast reply. Now, because it is unicast reply, the destination MAC is nothing but your host 1 VM1 MAC. The packet doesn't need to send to anywhere else. He already learned where that MAC is learned. So it directly sends the packet to your VXLAN port. Here, the unicast R packet will go to your VXLAN port. From there, it goes to your kernel. On your kernel encaps this packet, and then because it is a control plane packet, the packet goes out of your your physical port with an encap. And on the wire, it receives the packet as an encap packet. And remember again, here it is a control plane rule. So the packet coming from your tap 1 will directly go to your port 0. Now the reply has been sent from your VM1 of host 2. The packet came onto your physical port. Again, this reply has been, it's a VXLAN packet where inner packet is still an R packet. The packet is still considered as a control packet. It goes to your tap 1 where the decap happens. From there, it goes to your OVS. Here again, similar MAC learning happens where a host 2 VM1's MAC learning happens on VXLAN port. And we go ahead and program our backend with a rule saying that host 2 VM1 MAC should go should go by an encap mechanism. And also the OVS sends this packet back to pipeline or your tab 0 port, because the MAC is already learned the destination MAC. It looks at the destination MAC and send the packets to tab 0 port where the VLAN encap where the tagging will be removed from your packet and the packet will be sent to your VM1. Here the ARP request sent by your VM1 of host 1 received by VM1 of host 2. He replied back. The packet came back to your VM1 of host 1. So now ARP is done. Now any going forward, any data packet that needs to go, it doesn't hit any of these tap ports. The packet directly comes to on your pipeline. Based on previously programmed rules, the packet will be directly forwarded onto your physical port 0. So all these forwarding of packets will happen only because it is a control packet. So this is what we have. This is a gist of what we have discussed till now. So the underlay intelligence is taken from kernel, where your Linux networking underlay intelligence is taken from the kernel, and overlay intelligence is taken from your OVS. And we are using GNMI CLI to program all our ports. And these the ports are also differentiated, like vhost user port and the control port for your tap port. And these ports are also used not just for so in our current case, we didn't see any ECMP or any FRR. We just saw a single routing port. These ports can also act as your routing ports, and where you can send the packets out of your multiple ports, and hashing also can happen. And these are the ports that we are supporting. And for Dan's question, so this is the CLI that we have provided. How do you bind your physical port to your OVS, like or your control plane or P4 OVS? So the physical ports BDF will take, and we use this CLI where we say this is the physical port, and I want a corresponding control port for that, and these are the CLI that is used to bind that. It is not a actual bind, but logical bind where you can configure rules also to say that your physical packet coming on a physical port can land on your control port. Yeah, so that's all I had. Over to Nupur. So where we can see all our packet moving across on your VLAN learning and VXLAN learning happening.
Thank you, Sandeep, for explaining how the kernel cone plane acceleration works via P4. Let me go ahead and share my screen.
So just for the time check, Dan, it's okay, right? Since we are recording, it's okay to go over a little bit.
Yeah, absolutely.
Okay.
Can you see my screen?
Yes.
So today
Yes.
I'll be demonstrating the Linux networking scenario which Sandeep just explained. So for the better visualization, I have color coded the terminals. On the top left, I have P4 OVS running on the host 1. On bottom left, we have a window which will be used to set up the topology which was just explained. On top right is the VM1 which is spawned on vhost user port on host 1. And on bottom right, we have host 2 where we are leveraging the VXLAN kernel stack for our demo purposes. So in the interest of time, I've already started P4 OVS on the host 1. As you can see, the OVS DB server is running and OVS vSwitch daemon process is running. And let's take a quick look at the topology. So these physical ports, right now we are using the 10 gig Intel 10 gig ports. So to be for these ports to be used by the DPDK pipeline, we need to expose these ports to the user space IO. So right now we are using the VFIO PCI driver to expose this ports to the user space IO, as you can see here. And the next step will be to create the physical ports which Sandeep just explained using GNMI CLI and the corresponding tap ports, and then the tap ports which acts as a control port for your VM1 and VM2. And then we'll go ahead and create these VLAN port representers which are used for the control plane mapping. Then we'll go ahead and set the pipeline for the DPTK target and create this VXLAN port, which creates the VXLAN sys 4879 kernel port. And then we'll go ahead and program the rules for the control plane processing. So I've already created the VM1, which is on top of vhost user 0, which has the IP address 9901. Now let's go ahead and create the port. So I have the scripts for that. Let's take a look what the script does. So the first set of CLIs are to create the physical link ports. We are using the OpenConfig GNMI CLI utility to create the ports. Here, since these are the physical ports, the device type will be physical. And the corresponding control port is tap1, which also acts as a tap termination port for this physical port. Here you have to specify the PCI BDF for the port itself. And then the packet direction network means that this port is capable to receive traffic outside network. And the port type will be link. So we go ahead and create the ports for both port 0 and port 1. The second set of CLIs are to configure the tap ports. So the device type will be virtual, and you can specify the name of the tap port, and the port type itself will be tap. And then we go ahead and assign the IP address to the tap1 interface. So let me go ahead and create the ports. As you can see, as previously explained, as soon as the route was configured on the tap1, we see that since we have subscribed to these notifications, switch link was triggered and route entry was created. The next step is to actually configure the pipeline itself. So let me go ahead and do that. Before that, so right now, I have generated this Linux networking binary executable using OVS Pipeline Builder utility, which gets installed as part of P4 OVS installation. And we are using the P4C compiler with DPTK target and PNAS architecture to generate the artifacts required for this binary executable. So we go ahead and set the pipeline and add the bridge, which was mentioned earlier, to using OVS vsctl. The next step is to create the VXLAN port itself. So we are using OVS vsctl utility to create the port. And since the tap termination port is your tap1, the local IP is your tap1's IP. And on the other side, the tap termination port has the IP address of 40.1.1.2, and the destination port we are using is the standard VXLAN port 4789. Since we are listening to the netlink notifications for the VXLAN port creation, you can see that we go ahead and program the SI triggers the switch API, and we go ahead and program the VXLAN encap mod table with action as VXLAN encap, which is used for encapsulating the packet. And the other table which we program is IPv4 tunnel term table with action as decap outer IPv4, which is used for decapsulating the packet. Now, next step is to configure the control plane rules. So let me go ahead and explain what the rules look like. So the first set of CLIs are to create the VLAN port representers, which were VLAN 1 and VLAN 2. So we need a port representer for each VM. So right now in our setup, we have two VMs configured. So we'll go ahead and create VLAN 1 NetDev and VLAN 2 NetDev on top of tab 0 port and add them to the OVS bridge. That's what these steps are doing. The next step is to configure the control plane rules for control packets coming from the overlay network. So we are using OVS-P4 Cuttle utility to program the rules, and this utility expects us to use the target data path index, which is nothing but a unique identifier for every port. So let me quickly show you what it means. So we have the CLI to query the target DP index for each port. So I'll just show you an example for tab 0 port. So we can see that the target DP index for the tab 0 is 6. So similarly, you can query the target DP index for all the other ports, and this is what the target DP index comes out. And let me go ahead and explain the rules. So the first set of rules are for the control packets coming from the overlay network. The first rule is if any TX control packet is coming from VM1, which has target DP index 0, pipeline should add a VLAN tag 1 and send it to your tab 0 port, which has target DP index 6. So we go ahead and program the handle TX control packet table with action as push VLAN forward. And the VLAN tag itself is 1, and send to port will be port target DP index 6, which is your tab 0. And on the other hand, if any TX packet control packet is coming from tab 0 port with VLAN tag 1, pipeline should just strip the tag and send it to your VM1. So to reflect that, we go ahead and program the handle TX control VLAN packet table with action as pop VLAN forward. And the next set of CLIs are for your VM2. Then the second set of rules which we program are configuring the rules for the control packets coming from the underlay network. So basically that will be anything coming from your physical port 0 or port 1, and anything coming from your tab 1 or tab 2. So the first rule says that if any RX control packet is coming from your physical port 0, then it should be sent to your control port tab 1. So we go ahead and program the handle RX control packet table with action as set control destination. And similarly, on the other hand, if it's a TX packet coming from tab 1 port, it should be, if it's a control packet coming from tab 1, then it should be sent to your corresponding physical port 0. So you go ahead and program your handle TX control packet table with action as set control destination, and provide the correct target DP indexes. The next set of CLIs are for your port 1, physical port 1. So let me go ahead and configure the rules. And as you can see, as I configure the rules, they are getting programmed on the DPDK backend side. Okay, at this point, we are done with creating the topology for host 1. And on host 2, we are leveraging the VXLAN kernel stack, where we have created the VXLAN 0 port on top of the physical port, which has IP address 40.1.1.2. And the IP address of the VXLAN 0 port is 99.0.3. And the remote IP address for this VXLAN 0 port will be your tab 1's IP address of host 1, which is 40.1.1.1, and the destination port used is the same, 4789. So before I run the scenario, let's see if actually this VM1 has any intelligence to reach 99.0.3. As you can see, there is no ARP entry visible here. So let me go ahead and start a TCP dump on tab 1. And similarly, I'll start a TCP dump on tab 0 as well to see what's going on. So I'm going to ping 99.0.3, which is on host 2 VXLAN 0. And as you can see, as soon as the entry becomes reachable, the ping goes through fine. So let's see what happened in the background. So the first thing is, as Sandeep explained before, VM1 will initiate a broadcast ARP request. And since we have added a rule for any control packet coming from VM1, add a VLAN tag 1, send it to tab 0. This broadcast ARP request asking for a MAC address of 99.0.3 is visible on tab 0 port with VLAN 1. And this packet will reach to the OVS bridge and send it to every other port other than tab 0. So we see this particular request on tab 1, as well as VXLAN sys-kernel port. If VXLAN sys-kernel port has the intelligence of the underlay connectivity, it will go ahead and encap the packet. If it doesn't, then it will go ahead and send out the request, broadcast ARP request, as to establish the underlay connectivity. So on tab 1, we can see that a broadcast ARP request to establish underlay connectivity has been sent out. And we have received a unicast ARP reply from host 2 itself that, okay, 40.1.1.2 is at this particular MAC address. Once VXLAN kernel port has established the underlay connectivity and it has all the details to encap the packet, what it will do is it will encap the original broadcast ARP request, which was initiated from VM1, and send it out. So you can see that here, this particular packet is your outer header, 12B5 is your destination port, and this particular packet is your original broadcast ARP request, which was initiated from your VM1. Since so right now this is on tap 1, because of the control plane rules which we have programmed, if any control packet is on tap 1, it should be sent out to your physical port 0. From your physical port 0, it will reach your host 2, and host 2 will send a unicast ARP reply saying that unicast ARP reply responding with the MAC address of 99.003, which is 3AAD. And as you can see that we have received a unicast ARP reply. Again, it is an encapsulated packet. Now, since this port is also a TEP termination port, the packet will be stripped out and sent to your VXLAN kernel port. Once it is in reach VXLAN kernel port, it is in the control of OVS, where the MAC learning for your VM1 has already happened. So OVS already knows that if the destination address is VM1's MAC address, then the packet should be sent to your VLAN 1 netdiff. So you can see that here, that on tab 0, we see a packet with VLAN 1 tag, and the unicast ARP reply is seen here. And based on the rule programmed, if any control packet is coming from tab 1 with VLAN tag 1, sorry, tab 0 with VLAN tag 1, the pipeline will strip the tag and send it to your VM1. And that's how the connectivity is established. So let's see if you can see the intelligence here, that this particular VM already knows the MAC address of 99.03. So once this intelligence is programmed, then any further data packet will not go through any type of control packet processing, and it will hit the P4 tables explained earlier. We can also see what tables are hit and any stats using the DPDK pipeline CLI. So we are leveraging a DPDK debug CLI to look at the stats. So let me go ahead and show you the stats. As you can see, the number of packets and bytes are increasing here, and this CLI also allows us to see which tables are being hit and which actions were hit. So as mentioned earlier, any packets which are going out, we will hit a VXLAN encap mod table with action as one VXLAN encap for all the 172 packets which were sent out. I think one packet was dropped while the ARPN2 was being processed, but all the other 172 packets went through fine. And on the other hand, for the RX side, we will hit IPv4 tunnel term table with action as decap outer IPv4. And similarly, for the underlay connectivity, we go ahead and program the neighbor mod table with action as set outer MAC. So in this manner, you can use this utility to see which tables are being hit. And also this utility provides us to look at the contents of the table itself. So let me go ahead and show you the example. So I have just queried the contents of L2 forward TX table. So we can see that there are 3 entries available in the L2 forward TX table. So this particular MAC address is your VM1's MAC address with the action as L2 forward and sent to port 0. This particular MAC address is your tap 1's MAC address with action as L2 forward and sent to your physical port, which has the target DP index 2. And this MAC address is your VXLAN 0's MAC address with action as sent tunnel, since this port can be reached only via encapsulation. So this way, you can actually query the content and see what's going on in on the DPDK backend side. Thank you. This concludes the demo for Linux networking VXLAN scenario. Thank you. Over to you, Namrata.
Thank you, Nupur and Sandeep, for the great deep dive and the demo. It works. Everything works together very well. I just have, so if there are no more questions, I'll just go over the summary slide. So this is the summary slide. So what I wanted to say here is that we have moved P4OVS completely to open source now, open source development now. So you'll see a lot more traction there. And a lot of big features and rich patches. We basically ported. I think there's some mistake here. Please ignore that. So we've end-to-end Linux networking, and then control plane flow is working, port management, port and flow counters. We have TDI integrated. You'll see PTFs are added, and UTF framework has been created as well. So in the Jenkins CI/CD, we'll be enabling the PTF soon for the pre-commit stuff. So, and then we have Intra P4D. We are planning how to start Intra P4D in open source itself. We'll have the first small commit, and we'll go from there. It won't be like P4OVS huge commits coming in. And then thank you so much for attending. Here are some useful GitHub links. OVS, we have the kcontrol kernel control. Then we have the Linux networking P4 file link, and P4C and SCI. Thank you.
Any other questions? Okay, I think we can stop the recording. I think it would be an interesting follow-up. Another comment on the Slack was to maybe have some more help on how to onboard, like how to bring all this up and set it up. I think we could maybe do another presentation, or it would be great to be able to really easily be able to replicate the demo, because the demo is awesome.
So I forgot to mention that Newport has actually yesterday created a PR with huge documentation on how to bring up the Linux networking and how to use P4OVS to bring all this up actually. So that PR has not been merged yet. We still have to review it, but it's there on OVS.
Okay, that's exciting. So yeah, maybe we could do a presentation on that. Just go through it and maybe do a little tutorial on how to set everything up, because there's a lot. So this is great. Thank you so much.
Okay, thank you.